Today's episode is all about the Thalamic Reticular Nucleus, or TRN. In the previous episode, about sonic hedgehog and inhibitory neurons, we mentioned this nuclei that surrounds the thalamus for inhibiting signals or noise. The TRN is a shell designed to quiet unnecessary noise coming in to the thalamus. Remember, the thalamus receives all sensory inputs, and it's on a constant feed-forward, feedback loop with other areas of the brain. We'll review this nuclei in good detail and use a security guard analogy for each type of sensory processing and nuclei that makes up this shell known as the Thalamic Reticular Nucleus. This is all GABAergic, all inhibition. The more I think about it, the more the TRN is like a shield or armor. The TRN is a critical brain structure composed of GABAergic neurons that envelopes the thalamus, acting as a gatekeeper. I know, another analogy here, but it all fits. They all make sense. For this thalamocortical communication, the TRN modulates sensory processing, attention, memory consolidation, sleep-wake transitions even, and brainwave generation, with a significant implication to the autistic phenotype, where its altered function contributes to cognitive strengths such as strong learning ability. Remember, the biology that gives us autism allows us to be comfortable inside of ourselves. This shell, this TRN, with the autistic phenotype, prevents all of that outside noise, all of that outside external insults and care. It's also responsible for some of the visual thinking. However, it also implicates some challenges, such as sensory hypersensitivity, as discussed in the previous episode, and impaired integration. The TRN is a very thin, sheet-like layer of GABAergic neurons that surrounds the lateral and interior thalamus, and it forms a reticular shell between the thalamus and the cortex. Remember from last week's episode and a previous episode all about the parvalbuum interneuron. This is the major neuron here within this TRN shell. Remember, the parvalbuum interneuron is very fast-acting, fast spikes for precise inhibition. Remember the GABA-A receptor in comparison to GABA-B. And a small subset of the somatostatin, SOM neurons, for a more broad modulation. The receptors here are the GABA-A for the fast inhibition, and GABA-B, more with the somatostatin for the slower inhibition. Let's review some functional goals of the TRN. One, of course, is sensory gating. This is the major one. So enhancing signal-to-noise ratios, inhibiting irrelevant activity, and even prioritizing salient stimuli. For example, visual patterns over the background noise. So different sensory organs there. Attentional modulation, brainwave generation, sleep-wake regulation, cross-modal integration, so coordinating activity across sensory and limbic circuits for integration of perception and behavior. It's kind of helping coordinate or bridge the limbic areas in the cortex. We'll talk more about that later. Neuro-overload prevention. This is huge. We'll use a little security guard example at the end of the show. And it's also a support for the thalamus. The TRN helps the thalamus by sharpening signals, coordinating timing, preventing overexcitation. And this is enabling flexible processing, So it enhances the thalamic efficiency, and that's a big part. So what signals come in to the TRN, the afferents, or inputs? Well, it receives inputs from the thalamus itself, excitatory, glutamatergic inputs from relay nuclei, such as the lateral geniculate nuclei, remember for vision, and the medial geniculate nuclei, which is for auditory, and the ventral basal and the medial dorsal via AMPA and NMDA receptors, which is organizing for modality-specific processing. We'll have a whole episode on those excitation neurons, just like we're doing for the inhibitory neurons. It receives cortical inputs, again more excitatory inputs from cortical layers, especially 6 for the sensory and prefrontal cortex, enabling top-down control of attention and sensory gating. We'll talk a lot about the sensory gating. It's a good overarching theme and description of this shell. And also, a favorite of mine, the basal ganglia inputs. Inhibitory GABAergic inputs from the globus pallidus external, GPE, and the substantia nigra pars reticulata. Remember in the basal ganglia episodes, these two little nuclei, the GPE and the SNR, are pretty similar in function. And this modulates motor and cognitive processing. Now, the basal ganglia is a major region of interest for us here. Remember when we discussed the basal ganglia nuclei? There's 5 different nuclei there. And there's an additional assistant for the thalamus, which is sort of like the TRN, the subthalamic nucleus. This is another assistant to this thalamus. The basal ganglia role here with the TRN is some of the functions are action selection and suppression. So a normal role, a normal brain, let's say, the basal ganglia disinhibits the thalamus, and the TRN will send tonic releases of the neurons for sustaining adaptive behavior. However, in the autistic phenotype, there's an excessive TRN burst, so a difference between tonic firing and burst firing. And this oversuppression will lead to repetitive stereotypies. You know that with the autistic phenotype. Sensory motor gating. The TRN here in the normal brain filters thalamic input, let's say from the ventral anterior or the ventral lateral. But for the autistic phenotype, the TRN is hyperexcitability and sensory overload, and underfiltering causes this so-called hyper and hypo sensitivity, well known and understood in the autistic phenotype. The basal ganglia to the Thalamic Reticular Nucleus is also involved with cognitive flexibility. You know about this with the adaptive responses. We talked a lot, good detail about this. Major regions of interest here are the medial prefrontal cortex, sending signals to the input areas of the basal ganglia, called the dorsal striatum, and this will orchestrate the basal ganglia for the no-go areas, and it's kind of conducting what we do next. This is huge in the autistic phenotype, a so-called lack of adaptive responses. Remember, the medial prefrontal cortex is essentially conducting these movements and our healthy responses to this very unpredictable and chaotic social world. So, depending on the projections coming in from the prefrontal cortex, especially the medial part, and even the dorsal lateral part, we talked about these two regions in great detail last episode. These connections here will determine where the cells and signals will connect to the dorsal striatum, and this provides meaning Okay, this is happening because these cells are active. So this is what I do in response to that. These specific signals and connections from the prefrontal cortex to the dorsal striatum will house our movements, what we do. Remember, the prefrontal cortex is a rule-setting machine. And we need a flexible rule-setting type of machine, having different skills available to us for different situations. Now, you know about this with the autistic phenotype. Very rigid. So these signals coming into the dorsal striatum is also very rigid. We only have these limited amounts of kind of response types. And this is very big here. These are the neurocorrelates and the cellular functions of the lack of adaptive responses, the rigidness, the black and white thinking, and so forth. This is all happening here. So with this cognitive flexibility, for the normal brain, let's say, the TRN switches thalamic output. So it can just, remember we talked about action selection. This is all coming together here. For the autistic phenotype, we have those rigid routines and the poor task switching. This is why this basal ganglia to Thalamic Reticular Nucleus connection is just downstream from those prefrontal cortex to the basal ganglia inputs. So salience, remember we've discussed the salience network as well. I know a lot of different kind of nomenclature and terminology here, but it's really not that difficult. So what is salient to us? Where do we want to spend and send our attention? For the so-called normal brain, the TRN is helping mark social and reward cues. This is very big in how mammals, complex living organisms kind of navigate the society based off of cues. In the autistic phenotype, there's this so-called blunted social motivation here and very abnormal kind of reward processing for the outside world. In addition, this TRN here, as we just described it over the last couple of minutes, it can cause us that so-called stuck feeling or repetitive actions. So maybe a lot there about the basal ganglia and the Thalamic Reticular Nucleus connection and interaction. So let's get back to the afferents. There's interactions with the major neuromodulation inputs, the neuromodulators that we talk about and you probably know about, such as cholinergic acetylcholine from the basal forebrain. Remember, the nucleus basalis of my NERT is a hotspot for acetylcholine. And serotonin from the raphe nuclei, and norepinephrine from the locus coeruleus, and dopamine from the ventral tegmental area, VTA, and the substantia nigra pars compacta. Remember, this is different than pars reticulata. Reticulata is all GABAergic. That's helped modulating the basal ganglia no-go area. The substantia nigra pars compacta is a seat of dopamine. Remember, it's in the midbrain, the mesencephalon. This releases excitatory and inhibitory dopamine. And these inputs from these neuromodulators regulate firing modes, such as tonic or burst firing. This is very huge. This is at the heart of how we operate, or these firing modes and brain waves. It's really underrated here, in my opinion. So some of the efferents, the outputs. What does the TRN do? Where does it send information to? One, there's a feedback inhibition. This is a so-called closed-loop control of the corticothalamic axons. Excitatory neurons, pyramidal neurons to be exact, project to both the relay nuclei of the thalamus, such as the lateral geniculate, and the TRN. So the excitatory neurons coming in from the cortex is received by various areas, various nuclei within the thalamus, such as the lateral geniculate and other subdivisions here, and the TRN. And these nuclei within the thalamus itself are interacting. They're sending information back and forth to each other. And the TRN will receive that information and then decide to shut it off. It just turns it off. It's disinhibiting. And this is purposeful for sharpening sensory tuning and regulating attention, suppressing noise, and promotes oscillatory rhythms. This is huge for sleep spindles and gamma waves. In addition, another efferent interaction here is a feed-forward inhibition, or a so-called open loop modulation. There are some ascending sensory pathways here from the brainstem or the retina that sends collaterals to the TRN before reaching relay nuclei. So it's kind of privileged here. The retina, of course, massive amounts of visual input and sensory coming in from the retina. And also the brainstem, this so-called major highway. The brainstem is very underrated as well. It's a major highway here of information from the brain, from the body, and just interacting here. It's just making sense of so much. We'll talk more eventually about the reticular formation. Remember, this is different than the thalamic reticular nuclei, but the reticular formation within the brainstem has two major pathways: ascending sensory pathway and descending sensory pathway. But for this example, the region of interest for us is the ascending sensory pathway. And the TRN will then inhibit relay neurons, and it delays or sculpts the sensory interaction. The function here is controls gain, timing, and salience of the incoming sensory input. It's kind of like it's privileged here. It's getting first privilege information of what is happening, so we can stay ahead of any unwanted stimuli, or unwanted things from the environment, or signals from within ourselves even. Another major efferent and role of the TRN for the outputs is regulating burst versus tonic firing. And this is huge, as we just discussed earlier. The TRN neurons switch between burst mode, which is for strong inhibition, promoting sleep, seizures, or sensory suppression, or tonic mode, sustained inhibition, which helps fine-tune attention and sensory discrimination. What do you want to pay attention to? Remember, just imagine if the thalamus had to discriminate all of the sensory inputs coming in from the environment: vision, hearing, taste, touch, etc. There is no way that you'd want that. In short and in summary, the TRN is a major dynamic gate that is central to state-dependent processing, meaning between sleep and wake, or something like attention versus distraction, signal to noise. So you might ask, and you ought to ask maybe, what is the thalamic reticular nucleus made of? I'm not saying GABAergic, but let's zoom in to the thalamic reticular nucleus. What is it made out of? What is each area trying to accomplish? That's a good way of asking yourself a question about our biology. Why is it there, and what is it trying to accomplish? Well, the TRN has different sectors. We are going to say it has four major sectors here, four major kind of hubs or responsibilities. One is the visual sector. The second is the somatosensory sector. The third is the auditory sector. Remember last week we talked about V1, S1, and A1. This is what's happening here. This is where we're going into. And the last and the fourth sector is the limbic sector. So the visual sector is located in the rostral Thalamic Reticular Nucleus, and it's adjacent to the lateral geniculate nucleus, which is the major relay station here, one of the first stops for vision. And this is using, no surprise, the parvalbumin interneurons, and it's also using the VIP interneurons. Remember the vasoactive intestinal peptide. And it's using all three of the GABA receptors, A, B, and C. A for the fast inhibition of the lateral geniculate nucleus. So it's just kind of quieting visual distractions. GABA B for the slow inhibition, for the sustained modulation, trying to help you maintain attention. And GABA C for sustained tonic, like inhibition, for fine-tuning that visual gating. How long can you sustain your attention on a visual input? Think about children doing the staring contest. This is a good example here. Children doing the staring contest will utilize probably GABA B and definitely GABA C in order to just quiet themselves while they're staring at you. How long can you sustain that without being uncomfortable? Functions of the typical brain is the sensory gating. No surprise, we just talked about the staring contest. The gamma oscillations. This visual sector helps drive gamma power in the lateral geniculate loop. Lateral geniculate to visual cortex 1 loop. And this supports visual feature integration. And synchrony facilitates gamma synchrony between V1 and downstream dorsal lateral prefrontal cortex for visual cognitive integration. What's happening in the autistic phenotype is a reduced inhibition here. So the decreased parvalbumin interneuron, with especially GABA A and GABA C receptors, impairs lateral geniculate gating. And this increases excitatory input to visual cortex 1 and elevates gamma power. We talked about this a lot, and I hope people have a good takeaway here. The sensory processing is mostly gamma, even higher gamma, and this is one of the mechanisms by which that happens. Remember visual thinking and attention to detail. This is huge here. You know about how eye contact is pretty much a no-go for the autistic phenotype, especially for me, and as I've learned about others and talked to others, during speaking. Eye contact during speaking is a huge problem. There's so much happening. Remember the B-movie example. The sensory processing in the outside world is chaotic. Carl Deiseroth calls it a fire hose of information, a torrent of information. It's like a machine gun, a torrent. This is very accurate. If that's not you, you will have no idea what it is or what it feels like. In addition, there's a disrupted synchrony. So that reduced gamma synchrony between V1 and the dorsolateral prefrontal cortex impairs the visual cognitive processing. We just kind of discussed that. But V1 to the dorsolateral prefrontal cortex is very long distance. The dorsolateral prefrontal cortex is essentially at the very top, as far out as you can go. And V1 is at the very bottom back of the occipital lobe, right above the midbrain. It's a very long distance there. And also there's a disruption in the autistic phenotype with brain-derived nootropic factor influence. This is mostly excitatory. We'll talk a lot about this in the excitation episode. But this really amplifies that hyperactivity and sensory processing. And you should also remember the social cues now. You think you know about autistic phenotype and the social cues. This is all happening here as well. So the somatosensory sector, S1. This is in the central Thalamic Reticular Nucleus. And it has connections to other areas of the thalamus, excitatory inputs from a so-called ventral basal complex, and GABAergic projections back to the ventral basal complex. In the cortex, there's a bidirectional with S1 and the secondary somatosensory areas. It also uses inhibitory neurons, of course, parvalbumin interneuron, and somatostatin and the VIP. So it's using 3 of the inhibitory neurons we discussed before: parvalbumin, somatostatin, and the VIP. And the major region of interest here is kind of modulating and gating tactile, filtering out irrelevant touch stimuli. And it's also helped driving gamma oscillations to the VB, the ventral basal, and the S1 somatosensory sector loop. These are communicating back and forth for tactile discrimination. And it supports gamma synchrony with anterior insula for sensory emotional integration. A big part is that insula, especially the anterior insula. Major region of interest with the parvalbumin episode is the anterior insula. So what about the autistic phenotype? There's an impaired parvalbumin inhibition, so that increases the ventral basal activity and elevates gamma power and the S1. So you're thinking about touch responses. Reduced synchrony with the anterior insula impairs sensory emotional processing. And because of the lack of inhibition, this will amplify excitatory inputs from the S1. So tactile hypersensitivity is huge here, with downstream deficits, which impair synchrony with the anterior insula, affecting emotional processing of touch, impacting social interactions, discomfort with physical contact, if you will. The third sector, auditory sector. This is in the caudal TRN, and it's adjacent to the medial geniculate nucleus. You should probably have guessed that because of its auditory roles here. So the connections to the thalamus, excitatory inputs from the medial geniculate nucleus, and then the TRN will send back GABAergic projections to help balance the auditory stimuli coming in. And also to the cortex as a bidirectional with the auditory cortex 1 and the superior temporal gyrus. We will talk about autism and the auditory cortex. We'll do a whole episode on that soon. This sector uses the parvalbumin interneurons. Remember, these are the most dense. These are the most common type of inhibitory neurons. So no surprise there. And this also is modulated by the somatostatin interneuron and the VIP interneuron. In typical brains, this inhibition of the medial geniculate nucleus is for the auditory sensory gating, filtering out irrelevant sounds, and drives gamma oscillations in this medial geniculate nucleus to A1 cortex loop for auditory featuring and integration. And it supports synchrony with the dorsolateral prefrontal cortex and the superior temporal gyrus for auditory social processing. In the autistic phenotype, that reduced parvalbumin inhibition increases the medial geniculate nucleus. So it cannot have that push-pull tactic. And this will elevate gamma power in our auditory cortex 1. This disrupted synchrony with the downstream, or distal connection, I should say, and downstream. Actually, that works. Which are distal connections, remember. These are all distant. And this is that impairing that auditory social integration. So you should be thinking about that elevated gamma power in auditory cortex 1 enhances auditory detail processing and sensitivity to loud sounds. Very good hearing. Because of this, though, downstream deficits that reduce synchrony with those distal connections and processing speech in noisy environments. This is me. Remember, I used the example of the later Beatles songs. At the end of the songs, they're experimenting with different types of musical instruments and things that aren't musical instruments. They're just making noises out of like whatever they can find around the recording studio. This is me. This is clusters of noise and conversation in social settings are really amplified. I can pay attention to different clusters of conversations happening around me. And it's very difficult. It's very heightened and tough to sustain. So the last sector, the limbic sector. This is in the anterior, so the front of the Thalamic Reticular Nucleus, and it's adjacent to the medial-dorsal nucleus and the anterior nucleus. I know a lot of language there about the different subdivisions of the thalamus, but very relevant. Connections here with the thalamus. The thalamus will send excitatory inputs from these regions, the medial-dorsal and the anterior nuclei. And the TRN will send back GABAergic projections into the cortex as well, bidirectional with the dorsal lateral prefrontal cortex and the anterior insula and the orbital frontal cortex and the ACC, the anterior cingulate cortex. So the limbic sector here is responsible for a few additional major hubs, major nuclei here with the anterior insula, the orbital frontal, and the ACC. The inhibitory neurons here are similar, but we're going to add that 2-for-1 from the previous episode. Parvalbumin, no surprise. And then it's modulated by the somatostatin and the VIP. And we finally introduce again the calbindin and the calretenin in the dorsolateral prefrontal cortex and insula connections. Remember those last two, that 2-for-1, are very, very rare. In functional brains, the limbic sector is responsible for inhibiting the medial-dorsal nucleus for attention and emotional regulation. And this drives gamma oscillations in the medial-dorsal to the dorsolateral prefrontal cortex loop for cognitive processing. And it supports synchrony with the anterior insula and the ACC for emotional integration. Now remember, an early episode of the podcast, Autism and Adaptive Responses, and how the medial prefrontal cortex, ACC, and insula are in play here. When we are adaptive responding, when we are applying adaptive behaviors in society as we navigate life, the medial prefrontal cortex and the ACC lead the way. About minute 15 of that episode that I just mentioned really highlights this. There's a timestamp. MPFC, ACC lead the way. This means it's regulating those downstream behaviors. Remember the basal ganglia conversation that we just had. These inputs lead our responses, the skills that we have available to us. Whenever we are kind of heightened or hijacked, people will call it hijacked. The insula because it's receiving so much. It receives inputs from the brain states, what's happening in the brain with thought, and it's receiving inputs from the body, and it's receiving inputs from the environment. It has three sources, the three main sources there. The anterior insula is kind of privileged for that. This will lead the way and allow the subcortical areas like the amygdala and all of these things that are kind of making us be physiologically out of control. We'll start paying attention to the heartbeat, the heart rate, the rate of speech, our phase locking, and we will just kind of panic. Remember the para-aqueductal gray in the mesencephalon, the midbrain. There's different areas there with that happening here as well. It's what is regulating, what is controlling these circuitries, these neurocorrelates. This is a good example of this because you've probably even heard of the limbic system, which is mostly subcortical or all subcortical. And we can get hijacked with this. So some inputs or some functions of the autistic phenotype is impaired and or a lack of parvalbumin inhibition reduces the gamma power and synchrony in the dorsal lateral prefrontal cortex and the anterior insula. And this will cause overexcitation inputs from the dorsal lateral prefrontal cortex and amplify dysfunction. So with the autistic phenotype implication, there's a lot of cognitive and social deficits happening here. In addition, there are some OCD-like behaviors here because of the dysfunction of the medial dorsal and the orbital frontal cortex circuits that contributes to repetitive behaviors. So how strict is this TRN? What can get in and what has a more challenging time of getting in? The security guard examples. So with normal senses like sight, sound, and touch, the TRN exhibits strong control over these. It's like a guard checking every bag at an airport. Very detailed and deliberate checks. Can things bypass? Not easily. No. It's fully filtered. Thoughts and plans. The TRN has a kind of a weaker control over this. The TRN barely touches it. The guard waves the VIP interneurons through, and there's just a little delay. Can things bypass this? Can thoughts and plans bypass this? And the answer is yes, quite easily. If you think about evolution, the thoughts and plans aren't really an external insult. So evolution doesn't equip us with protecting ourselves from thoughts and plans. Evolutionarily, these are very critical and productive and necessary things. However, now, with the human's infinite capacity to just think, we'll spend all of our time, occupying our time, thinking about maybe good things, maybe bad things. Loud and painful shocks. Well, this is dependent. The TRN is a little limited here. It tries to, but it can fail. The guard can only stop so much. Too much input overwhelms it. Can things bypass it? Yes, it can break through. Wake-up chemicals from the brainstem. Remember the sleep-wake cycles. Well, the wake-up signals modulates the TRN. It's kind of dependent. It can be strict, or it can just be laid back. There's a lot going on here. There's a lot of variables with the sleep-wake. So there's rule changes. It's just too dependent. Pain and danger alerts. Well, this is kind of minimal. The TRN is minimal here. Because we have to kind of bias towards safety. And another way of looking at this is high intensity stimuli. Well, this can bypass the inhibition if there's life-threatening, if there's one trial learning type of things going on. The TRN is very limited at this point because remember the evolution example. Security and safety typically wins. Visual attention can be. There's a lot happening with the visual inputs, so it's kind of dependent. But it's mostly yes, especially in the typical brain. Now, the autistic phenotype will pick out kind of subtle things in the environment without people even knowing that it's happening. That's a huge benefit. And that has a lot to do with the high gamma and the lack of gating here. So the security guard can just kind of depends on, maybe they have a buddy and they let him in. Nobody knows it. They just got this secret message or whatever. I have something exciting. I want to introduce a product unlike any other product available. A highlight is the product from Daylight Computer Company created their product based on these factors. The Daylight computer is completely blue light free. It has no flicker. Short wavelength flicker is extremely harmful for our eyes and downstream biology. Light flicker is constantly turning our central nervous system on and off. Essentially, it is like going to a light switch and repeatedly turning it on and off. The problem is, blue light and LED light does this, and it is so rapid you cannot even perceive this in real time. The Daylight computer is the lowest stimulation and foremost for sensory sensitive users. It is no question that the alternative product, especially when used at night, do not address or consider this in their product. It is so toxic to human biology. Big tech corporations have patents on how their short wavelength implicate the human nervous system. And a bonus, despite Daylight computer not having backlight, it is very functional for outdoor use. And of course, increased sunlight is always preferred. I am happy to offer a discount for the Daylight computer. You can use the code AUTISM for a $50 off discount. Again, use the code AUTISM and the discount code for $50 off. See the link in the show notes to Daylight Computer Company, or just give it a quick search in your internet browser. Use the code AUTISM for $50 off. I would like to mention Chroma, lights designed for humans. Chroma, a Seattle-based innovator founded by ex-NASA and Air Force engineer Michael Shapiro, is on a mission to enhance physical and mental health with purpose-built devices, unlocking peak human health, cognitive function, and performance. Shapiro launched Chroma to restore the natural light lost to screens in indoor living and delivers faster recovery, sharper minds, and better sleep. Their products hit hard. The Iron Forge speeds muscle repair with red and near-infrared light, while the Skylight mimics sunlight to boost sleep and energy. A standout, the Forge lamp is a portable gem that fires 660 nanometer and 850 nanometer light to energize mitochondria and heal tissues on the go. Remember the 4 red light chromophores on cytochrome C oxidase, frequently talked about in the podcast. This is why their products are built with military-grade durability that have lasting impact. Chroma's tech fuses precision and power. Gallium titride power supplies, smaller, cooler, and stronger than silicone. Provide flicker-free light that's easy on the eyes. High-powered LEDs target key wavelengths for skin, tissue, and cellular health, with smart heat management for the lasting impact. Every design decision Chroma makes serves a purpose: to create devices that are precise, durable, and effective for improving human life. Remember, humans use different wavelengths of light for different functions of life. Remember when I ask, what do you think light is? Chroma designs with our biology in mind, from sleep aids and wound healing to mitochondrial energy, full body lights and blue light blocking glasses. They are US made and Chroma ships globally and accepts FSA and HSA payments. Use Autism at checkout for a 10% off discount. That's Autism at checkout for a 10% off discount. If you are listening to the podcast, listening to the episode, please feel free to leave a review or rating. In podcasting, reviews, ratings, and downloads are huge, and I very much appreciate your feedback. You can contact me on X at RPS47586. We can discuss anything and everything about autism. I very much appreciate your comments and your interactions on X. You can check out the YouTube page for all the videos, full-length videos, shorts, and clips. You can email me, info.fromthespectrum@gmail.com. Thank you for listening to From the Spectrum podcast.